All right, hello everyone. My name is Alex Polanski, and I'm also looking for where I put that clicker. I put it in my pocket? Yes, I did. So yeah, I can imagine all the Galaxy people are thinking, oh boy, another planet survey talk. But today I'll be going into the latest installment in the TESS Keck survey series with our survey's mass catalog and data release. And so this is going to be including constraints for 127 planets and planet candidates, discovered by the Transiting Exoplanet Survey Satellite, or TESS. Also, this is my third KSM, but my first talk, so thank you for the organizers for providing the slot, and for all the hard work that they do to set all this up. So 30 years ago, at this point, the brand new WM Keck Observatory was finding itself in what I would believe the perfect place at the perfect time. This awesome photo is from 1987, showing just one of the Keck domes mid-construction, and just a few years later, we would actually find the first worlds around other stars. And one of the instruments that has been with Keck practically since the beginning is the high-resolution Michel spectrograph, or high-res. And it turns out that if you pair a 50K resolution spectrometer on a 10-meter telescope, you get one of the most powerful planet hunting machines in the world at the time. Fast forward to today, and we have over 5,000 exoplanets and counting. Around a fifth of those have been discovered through the radial velocity method. And of those 1,000 planets, nearly 20% of them have been discovered with our observatory, which I think is incredible. HiRes has contributed innumerable radial velocity measurements to planets discovered by transit surveys from TESS and Kepler. And this is crucial work because RVs tell us something that transit surveys generally don't: the mass of the planet. So why are masses so important? Well, first off, you can't really say anything about the bulk composition of a planet without knowing its density. Therefore, you need precise radii and masses. And it turns out for a planet of a given radius, sometimes that mass can vary by up to a factor of 5 between planets, so it's actually good to go out and measure these masses. Additionally, the planet's mass is key to understanding any observations of a planet's atmosphere made by flagship missions like JWST and REL. And for that, it's been recommended that you want to measure a planet's mass to around 5 sigma confidence. So masses are important, and this is where the TESS Keck survey comes in. So TKS is a NASA Strategic Mission Support Program made up of collaborators from multiple institutions stretching all the way from Hawaii to the Midwest. The survey itself was started about 3 years ago with a very well thought out target selection process that identified 86 TESS objects of interest, or TOIs, that were valuable across multiple different science cases. And this Venn diagram is just a very nice way of showing those different science cases and how those TOIs were shared among them. The ultimate goal of the survey was to measure precise planet masses for around 100 exoplanets. And this work was led by Ashley Shantos, who actually gave a talk on this at my first KSM. And I'm incredibly excited to be here talking about what is effectively the culmination of that work. So over the last 3 years, we've published around 20 papers detailing individual discoveries. You can see, please come to Jillian Murphy's talk tomorrow afternoon about one of them. But for 86 different systems, we can't possibly publish an individual paper on all of them. And so for that, we have the TKS mass catalog, which will be the data and planet mass release for our survey. In total, we took over 10,000 radial velocity data points spread between Keck High-Res and the Automated Planet Finder at Lick Observatory, all of which will be published in this catalog. All this RV data was also used in a very large and standardized RV fit to produce mass constraints for 127 planets and candidate signals. In addition, we also take the opportunity to try to assess TKS, so trying to understand how well we achieved the goals that we set out 3 years ago to do. And so with that, I can actually present the mass radius distribution for the TKS sample. So here we have the masses in radii for all known exoplanets with some decently precise mass in gray from the Exoplanet Archive, and then in blue we have the TKS sample. And so the size of the circles are scaled according to their mass uncertainty, so smaller circles indicate a smaller uncertainty in the mass. As you can see from the distribution, this will be one of the largest single releases of planet masses to date, and certainly one of the largest where that the mass has been determined through the same instruments and through a very homogeneous fashion. In fact, we will actually be increasing the number of planets between 2 to 4 Earth radii with a measured mass by around 50%, which I think is fairly incredible. In addition, your planet mass is only ever as good as how well you're able to measure your stellar parameters. So all of these planetary properties have been derived from updated stellar parameters that are more precise and uniformly determined in our TKS stellar properties catalog, making this one of the most self-consistent, I would say, catalogs out there as well. And so now we can go from sort of this eagle eye view down and zoom into the small planet space. And I'll start by putting each planet from the TKS sample up there. So they're color-coded according to their equilibrium temperature. Stars outlined in gold represent newly validated planets. So this work alone will be adding 32 newly validated planets across the TKS sample, either through mass constraints or statistical validation. We can throw up some typical sort of compositional tracks to guide the eye. And then finally, these blue contours are showing the exoplanet population as a whole around F, G, and K stars. So the TKS sample alone really tries to span nearly the entire parameter space of all known exoplanets. And we really do focus a lot of attention on that dense area, the sub-Neptune population. And as we go down to smaller and smaller planets, we really begin to stretch the capabilities of high-res. So high-res has a noise floor of around 1 to 2 meters a second, which means getting precise masses for the smallest planets is kind of a challenge, even with 100 nights of telescope time. But considering that measuring planet masses around F, G, and K stars, as opposed to M dwarfs, is fundamentally harder, high-res is still proving itself to be competitive even in this space. So we have all these masses, and the survey is essentially over. So the obvious question is, how well did we do? Did these observations result in the mass constraints that we set out to achieve 3 years ago? Well, in total, of our 127 planet sample, we were able to achieve a 5 sigma mass on 59 of them. If you're a little more generous with mass constraints and say 3 sigma, that goes up to 74. And I really want to try to emphasize how incredible this number is. Our survey was made up of very different science cases and very different science drivers, which inherently made measuring the masses of some planets a little more difficult. Examples include our stellar activity case, so we're targeting planets around stars that have high amounts of stellar activity, and our distant giant science case. Both of these were not primarily concerned with the TOI itself and getting a precise mass on that planet. And they make up, as you would expect, a lot of our underperforming TOIs. The TKS sample was not selected to be easy targets. We really pushed high-res to its limits, and it performed incredibly well. If we look at smaller planets, many of our significant mass measurements in the 3 to 10 sigma range are made up of planets smaller than 4 Earth radii. To put this into perspective, TESS's level 1 science requirement was to measure precise masses for 50 planets below 4 Earth radii. And that was an objective given to all the RV teams. The TKS survey was able to nearly achieve that goal all on its own with 38 planets below 4 Earth radii with at least a 3 sigma mass constraint. So with all these masses, we were also interested in how well commonly used mass-radius relations actually hold up. When selecting these targets, we assumed theoretical masses calculated from 2 mass-radius relations, Weiss and Marcy 2014, and then Chen and Kipping 2017. And now with the actual mass in hand, we can see how close to those predictions we actually were. So here I'm showing a 1-to-1 correlation plot. On the x-axis, we have the mass that we predicted 3 years ago, and then on the y-axis, we have what we actually measure. So for planets where we use Weiss and Marcy, we find that the agreement is fairly good. It's able to predict planet masses fairly well, and we even see very similar RMS scatter between the correlations as was found in their original Kepler sample. The story for Chen and Kipping, however, is a little bit different. We find that those mass-radius relations actually tend to underestimate planet masses by around a factor of 2. Now, this could be due to any combination of reasons, one of which is that there are actually fewer planets in the Chen-Kipping sample in this sort of size range. So they might not be too representative of the exoplanet population as a whole. Regardless of the reason, if you're planning another RV survey and you need to calculate mass estimates, it's good to take care with which mass-radius relation you choose to use. In addition, if you're, say, interested in good atmosphere targets and you need to calculate and estimate scale heights, and you need a predicted mass, if you're using, say, something like Chen and Kipping, you might actually be inflating your spectral features more than you should be. And so with that, I'd like to just throw up a few acknowledgements. Of course, we use a lot of data from telescopes on Mauna Kea, which is a huge place of cultural significance. I'm incredibly grateful to be able to use this observatory. When I first started in astronomy, I didn't think I would ever be able to be involved as heavily as I am with these telescopes, and I'm really, really grateful for it. And of course, I also want to thank the many COIs and observers in TKS and CPS, especially junior researchers who spent countless nights collecting a lot of the data pretty much all the data that made this survey possible. And I'm going to throw up my conclusions and takeaways, and thank you very much.